Alright, so now we're basically going to work through several examples of classic related rate problems that you're going to see. And what you really have to remember when you're taking a look at these related rate problems, probably the hardest thing after you get the skills of reading the problem and being able to interpret and knowing what you're actually looking for is actually coming up with a formula that relates your quantities together, because that's really kind of need to know all the math that you've learned up to this point, whether it's geometry or algebra 2 or pre-calculus. So there will be things coming in that we kind of want to play around with. Now, the first couple examples are focusing on the geometry type applications that we're looking at. So here's another one. We just did a rectangle. So now we're looking at, we have a right triangle whose sides are changing. At a particular instant, it has 30 and 40 inches. So this is going to be our when. So I'm just going to circle that so I know that I'm going to remember. I think that where it says sides here, I want to actually say legs are 30 and 40, just to be a little bit more clear what I meant by that. All right, we're given that the shorter of the two sides is increasing at 3 inches per second. All right, and that the longer side is decreasing at 5 inches per second. So those are some given rates that we have. So I'm kind of reading through the problem to understand it. And we want to know how fast is the area changing. So we're going to start with A. And this is kind of how I set up the problem. I'm going to kind of ask you the same questions we did in the first example, but this is the work that you would need to show. All right, so the first thing we notice, we're trying to find area. So A, area, identify the quantity that I'm interested in investigating. I need to put units. Since the sides are in inches, then the area would be in square inches. And I'm trying to find dA/dt. Okay, so I set that up. Then I go through and I say, well, let's get my other quantities that are there, my other variables and the rates that I'm given. Notice I'm ignoring the instant, the when, because that doesn't really affect any of this. I come into the second sentence, and I know the shorter of the two sides is increasing at 3 inches per second. So I need to kind of give myself some variables for this. A lot of times you will draw a picture at this point. I am not going to put in an actual 30 and 40 here. Do not put the when onto your diagram. You want these to be variables, and so it doesn't really matter to me what you use. If you want to use x and y, just identify it as x and y. These are changing over time. You have a triangle that is right, that's kind of important, and that one side, let's call x is the short side, so I'll say x, the short side, going to be measured in inches, and they've given me that it is increasing at 3 inches per second, so dx dt would be 3 inches per second. I identify the next quantity, y, which is going to be the long side, measuring it in inches, and they gave me dy dt is decreasing, negative 5 inches per second. So the initial part of the problem is to basically notice that I have my variables, I have the rate I'm looking for, the rates I was given, I have a little picture going over here, and then the last thing that I was given is the when, and the when that I'm interested in is when x equals 30 inches and my y equals 40 inches. So that's my when. So I identify the quantity and the rate I'm trying to find, the quantities and the rates that I'm given, and then I identify the instant. So this is just writing down the information from the problem. The very next thing that you're going to do is you're going to write down your quantity equation, your quantity formula, the formula that relates your variables together. So I have the variables a, x, and y, and then this requires you to have knowledge of geometry. How do you find the area of a triangle? So area equals 1/2 your base times your height. So I write my quantity formula down. I immediately follow that with my related rates formula. And how do I get the related rates formula? If I know the quantities, how do I relate their rates? I take the derivative implicitly. So you show that you're taking the derivative of both sides with respect to time. So we end up with dA dt equals, I'm going to have to use product rule here, so it'd be 1/2 x dy dt plus y times 1/2 dx dt. And don't forget to do, that's the common, if you use x as your variable, you have a common mistake of forgetting to do the dx dt part of that. But remember, we're taking the derivative with respect to time. So this is the most important formula that you have come up with. Everything that we do up until this point is basically identifying variables, given rates, and rate that I'm looking for, the instant that I'm interested in, maybe draw a picture to help me come up with the geometry of it, because a picture always helps when you're doing geometric figures. Get your quantity formula, get your related rate formula, and then you get the formula you're going to use to answer the question. What are we being asked to find? We're trying to find dA dt. I need to know x, dy dt, y, and dx dt. So at this point, plug and chug. We know that using the information that we have from above, let me just zoom out just a little bit. Let's try 100%. All right, so I have all the information listed up here, so I can pretty much go dA dt is going to be 1/2 the x, the when, 30 inches, dy dt, which is -5, plus my y, which is 40 inches at this instant, times my 1/2, times my dx dt, and dx dt is 3 inches. So once you get this part of the information down, then it's simply going to be a plug and chug. And so we simplify it out. You should end up with -15 inches square per second, because it's changing area. And then you always write the sentence that goes with the problem. So you're like, okay, what's the sentence? When the short side is 30 inches and the long side is 40 inches, the what area is doing what? Decreasing by how much? 15 inches square per second. And so we have the problem worked out for us. Now the second part of this is we want to know how fast is the hypotenuse changing. Okay, so for part B, now I need to have a variable for hypotenuse, so I'm going to call it, well, let's call it C, because we're like used to doing A, B, and C. So let's do C. I'm going to make that the hypotenuse. It's going to be measured in inches, just like everything else was. And what am I trying to find? dC dt. Now, since I already have this information up here, I'm not going to redo it. I'm going to keep my same x and my same y. Now, when I go to get a quantity formula, the only thing that changes here is now I need to relate the quantities x, y, and c together. And you're like, oh, it's a right triangle, so x squared plus y squared equals c squared. There is my quantity formula. And all I'm doing to get this, I'm using geometry. I mean, what information do I know about right triangles? So once I have that, then I have to find my related rate formula. So I take my derivative, 2x dx dt plus 2y dy dt plus 2c dc dt. Okay, so I get my related rate formula, and technically I should be writing the step where you take the derivative with respect to time of both sides. I was running out of room, so I was trying to cheat just a little bit. Add myself a little bit more room there. And so basically, now that I have the related rate formula, this is the important part. This is what our goal is. Once we have this formula, then all we need to do is plug and chug. So down here in our related, what are we asked to find? We are trying to find dC dt. That's that part of the formula. You could solve it if you want. And this should be an equals. now that I've zoomed in, see what I'm doing. Doesn't really matter. We're going to plug and chug. We'll solve for it after we plug and chug. So we plug in everything we know. 2. The x was 30. The dx dt was 3 plus 2. The y was 40. The dy dt was minus 5 equals 2 times, oh, wait a minute, I have a problem. I'm trying to find dc dt, but let's put a little star right there. I don't have a c to plug in. But that's when you're like, okay, wait a minute. I actually can figure this out, because let's do a little star over here on the side. We know a formula that relates the quantity together. We know that x squared plus y squared equals c squared. And the instant that we were looking at was x equal to 30 and y equal to 40. So can't we figure out what c is based on this given information? Yes, we can. So this has an extra step, as when I went to plug things into my formula, I was missing something. But you will have information on your paper to find that piece of missing information. So, and hopefully I'll just leave the arithmetic to you, that c is going to be 50. So we are going to fill that in. So now we've got everything we need, and the only unknown in our problem is dc dt. So we pretty much are going to basically solve for dc dt. And again, I'm going to leave the arithmetic of getting the number and dividing there for you. You do end up with that ending up being negative 2.2 inches per second. Okay, so I'll leave you to do the arithmetic for that. And then the last thing that we have to do is answer the question. So here's our when. Short side is 30 inches and long is 40 inches. What? The hypotenuse is decreasing by 2.2 inches per second. And so that essentially is this problem. So what we're basically talking about here is the idea that these problems are, in my opinion, they're not that difficult. What happens is you guys get confused on a couple of steps. One, you don't show your work very well. So this part is crucial to write down the quantity, what you're looking for, the quantity, the rate you're given, the quantity, rate you're given, and your instant. Your quantity formula, your related rate formula, and then plug and chug. And if there is anything you're missing when you go to plug stuff in, you come over on the side and you find it using information you already have written down. Okay? So kind of in general. Oh, I forgot. Oh, I did 2 pages in this because I left myself all that extra room so that I could do B. Let's just assume that I managed to get B in on the next page, because I was like, oh, there's a reason why I didn't have enough room here, because I had a whole nother page for you to actually put the information for B in there. I was trying to save you some room. So fix that if you want, but otherwise we're just going to go to this page, assume that we've done that part. Let's scroll down to the bottom and take a look. So in order to solve related rates problems, you just need to be organized. Identify that it is a rate problem because you're looking for how fast, be able to interpret the rates you're given and list your variables, and then be able to come up with a quantity formula, and then use your quantity formula to get your rate formula. If you are making a sketch, if it's a geometry problem, make sure that when you label things, that you label them as variables. Do not use the instant, the when, to plug in. Okay? The only time that you would not label something as a variable if it is something that is actually constant, that does not change the entire time. We're going to look at an example that has that in it shortly. Make sure you give your rates as d quantity dt so that you have them with the correct sign so that you interpret correctly what you're given. And identify your snapshot that you're going to use when you plug and chug at the very end. And then pretty much find the equation that relates the variables, your quantity equation. Take your derivative implicitly, okay? And then plug all your values in at the end and make sure you answer the question. The problem with finding the equation that ties everything together is geometry, areas, area formulas, right triangles, Pythagorean. You could have some trig formulas in there. General triangles, you might have law of cosines. All these formulas you've learned in your math classes up until this point are going to come into play, right? And then make sure you answer the sentence. Answer with a sentence. All right, we're going to do one more example in this little set of notes, just because this is another geometry problem. You have an oil tank that spills oil that spreads in a circular pattern. Circular pattern, so we're talking circles here. The radius increases at a rate of 50 feet per minute, so I'm given a rate, so I'll underline that. Given rate. And then the question is, how fast are both the circumference and area increasing? So I'm looking at how fast, so I'm looking for a rate. Let's call A the circumference and B the area. And then here is my when. When the radius is 20 feet. When. And then they have a third question. It says, if the depth of the oil is given by this, how fast is the volume? So we'll call that one C. So we actually have 3 parts to this problem. And let me just check. I did not give any more pages, so we're going to do 1 page for all the parts. All right, so we're ready to go. Let's start with A. What am I being asked to find in A? The change in how fast the circumference is changing. So my quantity is circumference. Measuring circumference in, where are we at? Feet, so feet. What am I trying to find? dc dt. All right. What variables are we given? R, which is our radius, measured in feet as well. And we're given dr dt increases at a rate of 50 feet per minute, so positive 50 feet per minute. Let's draw a little picture to go with this. I'm going to label this as R. Your spill, the circle, is getting larger as we go. All right, so just so that you can have a little visual of what's happening, here's my oil slick, getting larger, increasing at that rate of 50 feet per minute. Okay, the radius is increasing at 50 feet per minute, so the oil slick is getting larger. Just a little visual to go with our problem. Right? So we'll notice I'm not putting our 20 feet. I'm not putting 20 feet on here because this is getting larger. You visualize what's changing. As the radius gets larger, the circumference is changing, the area is changing, and so on. Right? So we only had one variable in this problem, so I'm pretty much ready to write my quantity formula. So my quantity formula is a formula that relates circumference and radius. Well, that's easy. Circumference equals 2 pi r. My rate formula, take the derivative of both sides, derivative of c with respect to t, excuse me, derivative of 2 pi r with respect to t. So my related rate formula, dc dt equals, remember this is a constant, so the derivative of a constant times r would simply be 2 pi dr dt. So here is our formula that relates our rates together. All right, so now we're ready to basically plug and chug. And we see that we don't really need a lot to plug in here. My dr dt is 50, so I pretty much go dc dt equals 2 pi times dr dt 50, or 100 pi feet per minute. Okay, so I get my units in. We answer the question. The circumference, and we need the when. I didn't use it because it didn't depend on it, but we do need to say it. When radius is 20 feet, the circumference is positive 100 pi, so increasing at 100 pi feet per minute. So there's my part A. All right. For part B, now we're looking at the area. So the only difference is now instead of circumference, I'm using area and I'm trying to find dA dt. So my quantity formula area of a circle is pi r squared. My rate formula, take the derivative of a with respect to t, take the derivative of pi r squared with respect to t, dA dt equals 2 pi r dr dt. So now we know that we have our related rates formula. We have what we're trying to find, so we're going to plug and chug everything else in. It's a very simple problem. dA dt equals 2 pi. I need an r. What was our time, our instant? The radius was 20 feet. So when the radius was 20 feet and I'm trying to do my dr dt was 50 because it was increasing. And then basically plug and chug, get your answer for the area, and we get 200 pi. And don't forget your units, feet squared per minute, because it's area over time. And then we answer the question for the second part. When the radius was 20 feet, the area is increasing at 200 pi feet squared per minute. So there's B, done. All right, now let's talk about C. All right, now for C, we are given some additional information. What I would like to do is now I'm talking about volume and there's a depth to the oil spill. So kind of picture-wise, let's think about what we're doing. Now I'm thinking of this oil spill kind of as a circular disc. Okay, so we have this, here's our radius, here's our depth. I'm just going to label that as D over here on the side. And what we're trying to do is calculate our volume of this. So now the quantity I'm interested in is volume. Volume would have units of cubic feet, and I'm trying to find dV dt. Okay, so I still have my R from above, and so I'm just going to rewrite this down so I have everything. R is my radius. That was being measured in feet, and dr dt was the 50 feet per minute. All right. Then I have my new variable that I need for volume is depth. Depth is going to be measured in feet, and really I kind of have two pieces of information here. I have the depth formula, which they're giving me right here. D of r equals 2r squared plus 1. So D equals 2r squared plus 1. So I actually have a formula for the depth. And if I needed a rate for the depth, I know this is kind of bad because I used lowercase d there, the derivative of D with respect to t would be the derivative of 2r squared plus 1 with respect to t. So even though, and let's just call this d prime, just because I have dt. Well, actually, it's all right. We can do dt. We know what we're talking about. That when you're looking at this, you might not have been directly given a rate, but I can get dt. I know that its formula is going to be 4r dr dt plus 0, because that's going to go away. So I'm kind of writing down my information. My variables, here's my information on my rates. Okay. Now, let's talk about a quantity formula. Quantity formula. The quantity formula is going to relate volume, radius, and depth. Well, this requires some geometry. The area of a circular prism like this is the area of the base times the height. So the area, or the volume would equal basically the area of the base, pi r squared, times the height, the depth, times d. Now you have two options for this problem. You can, because we have all this information up here, take the derivative right here, and you will have a derivative that involves the product rule and has r and d in it, and we'll have dr, dt, dd, dt, dv, dt, okay, which is perfectly fine. Or the second option when we are doing this problem is that we can, because we have a formula for d, we can substitute that in and kind of eliminate that in the beginning. You kind of have options. I'll show you both as you're working through this. So let's do option 1, just to show you kind of the difference. I'm just going to leave it as v pi r squared times d, and then I'm going to find dv dt. I'm going to take the derivative of both sides with respect to t. With respect to t, take the derivative of this with respect to t. I'm going to use my product rule because I'm going to do pi r squared together and then the d. So I would have the first times the second plus the second times the derivative of the first, 2 pi r dr dt. So I can plug and chug over here. I'm looking for dv dt, so here's my related rates formula. Circle that. I'm going to plug in what I know. I'm looking for, this is what I'm looking for. So we have dv dt equals pi. The r that we're interested in was when it was 20 feet, so 20 squared. I need to find dd dt, and you're like, oh, wait a minute. I got to do some extra calculation here. I have to find dd dt when my r was 20. So I do have a formula for that up here, so I'm just going to do it down here on the side. 4 times 20 times dr dt. Dr dt was 50. So that's going to give me 80 times 50, 400. If I can do mine, is it 400 or 4,000? I always get to these things and then like, wait a minute. So we have 80 times 50. All right, so we have 80 times 50, that's 4,000. So I can fill in my 4,000 here, plus my D. Oh, wait a minute, I don't know that one either. Let's put a star by that. There's a lot of extra work in this. You got to find all this information. I have a formula for D. D equals 2 times R, the 20, squared, plus 1. So we just have to figure that out. All right, so that's 801. So that's going to get filled in there. Times 2 pi times my 20 times dr dt, which was 50. So you have a formula. You just had some extra work. You had to actually find some pieces as you go. Whatever I was missing, I looked up here and I realized I had formulas for it. So I use the formulas that I have above. I calculate this so I can plug it in. I had to calculate that to plug it in. But at that point, now we're good. We're just going to hit our enter and see what we get. And it's some really nasty number, I think. I probably want to double check this. I'll do that. Let me double check what we actually get. You can plug it into your calculator, see what we get. All right, so verifying, we get 320, 2,000 pi, and this is volume, so it's inches cubed per minute. That's a lot of work. So that's option 1. Don't worry, don't care about leaving the R and the D in there. Look at how much work we had to do. This part, no difference in what we had before, just take the derivative implicitly, but we did have 2 items we had to calculate in order to find it. Now before I write the sentence, I'll write the sentence at the end. Let's do option 2. Option 2 is to take our formula, V equals pi r squared d, and we're going to substitute. We're going to eliminate one of the variables. So we're going to substitute in for this d, pi r squared times our 2r squared plus 1. So we're going to do this, and then I'm going to simplify a little bit because I think it'd make it easier. I don't want to use product rule. I'm going to make it 2 pi r to the 4th, just distributing, plus my pi r squared. So now I just have to do power rule. So now I'm going to take the derivative of v with respect to t, take the derivative of 2 pi r to the 4th plus pi r squared with respect to t. So we end up with a related rates formula of dv dt equals 8 pi r cubed dr dt plus 2 pi r dr dt. So that gets us to a related rates formula of this. Looks different than what we had above. But what's nice about this is now let's go plug and chug. So we're going to plug in, here's what we're looking for, dv dt. We have 8, we have pi. Our radius that we're plugging in was 20, our instant. Our dr dt was 50 plus 2 pi, my r 20, dr dt 50. And you're like, oh, wait a minute, that was a lot easier. In the example where I left the d in, I had to actually do 2 calculations in order to get everything I needed to plug and chug. Down here, once I took the d out by doing the substitution in the beginning, it actually worked it out to be a little bit easier because I didn't have to do any extra calculations. I had everything I needed from above. And so, and if you double check this, our 8 times 20 cubed times 50 plus 2 times 20 times 50, we should get the same answer that we got before, our 322,000 pi inches cubed per minute. So in general, let's kind of make this as a note to yourself. If you can simplify the quantity equation by substitution, eliminating a variable of some sort, do that. Simplify early and often, okay? Because that's going to make the problem into an easier problem. And then just to finish this one out, we should answer the question. The volume, don't forget the when the radius is 50 feet, the volume is increasing at whatever this value is, pi inches cubed per minute. All right, so these 2 examples, they're definitely just using geometry, okay? And they're definitely looking at this idea of what are some things that you could run into that make this a little bit harder. The first A, pretty straightforward. Nothing really funny about that one at all. Your second one, nothing really that funny about that one. Pretty much just quantity plug and chug. When you get to C was interesting because it's showing you this idea that sometimes you end up with another formula that you can use to find the rate. You have options that you can either leave the second variable in and take the derivative, or if you can eliminate the second variable using a given equation to you to make your quantity equation simpler, less variables, you want to do that. And it doesn't matter, it'll work out both ways. One way might be less work than the other.